Picture this. You're standing at the edge of something impossible. A shimmering tunnel of twisted spacetime stretches before you, its walls rippling with energies that bend the very fabric of reality. Through this cosmic doorway, you can see another place, maybe another planet, maybe another galaxy, maybe even another time. You take a step forward, and in an instant, you've crossed billions of light years. This isn't just science fiction anymore. This is the realm of serious physics, where the most brilliant minds on Earth are asking one incredible question. Could we actually build a wormhole? Einstein called them bridges through space-time. Modern physicists call them the ultimate shortcuts across the universe. Hollywood calls them plot devices. But what does the science really say? Today, we're diving deep into one of the most mind-bending concepts in all of physics. We'll explore how these cosmic tunnels could theoretically exist, why they might be the key to everything, from faster-than-light travel to time travel itself, and whether humanity could ever harness the power to tear open the universe and step through to the other side. The answer might surprise you, because while wormholes sound like pure fantasy, the mathematics that govern our universe suggests they could be terrifyingly real. But building one? That's where things get complicated. The year was 1935. Albert Einstein, the man who had already revolutionized our understanding of space and time, was working with his colleague Rosen on a problem that would echo through the decades. They weren't trying to invent faster-than-light travel or time machines. They were simply following the mathematics of Einstein's own theory of general relativity to its logical conclusion. What they discovered was extraordinary. Buried within Einstein's field equations, the same equations that predicted black holes and the expansion of the universe, was something unexpected. A solution that described a tunnel through space-time itself, a bridge connecting two distant regions of the universe, or perhaps even two entirely different universes. They called it an Einstein-Rosen bridge. Today, we know it by a more evocative name, coined by physicist John Wheeler in the 1950s, a wormhole. The name is perfect, really. Think about an apple with a worm tunnel through its core. If you're an ant walking on the surface, traveling from one side of the apple to the other means a long journey across the curved surface. But if you could shrink down and follow the worm's path through the center, you'd arrive almost instantly. Now scale that up to the universe itself. But here's where things get interesting. While Einstein and Rosen had discovered these mathematical bridges, they never seriously considered that you could actually travel through them. These were abstract solutions to complex equations, not blueprints for cosmic highways. That changed in 1988, when physicist Kip Thorne, the same man who would later advise on the movie Interstellar, published a groundbreaking paper. Working with his colleagues Mike Morris and Uwe Yurtsever, Thorne asked a deceptively simple question. What would it take to make a wormhole that you could actually use? Their answer launched 1,000 sci-fi dreams, and just as many scientific nightmares. From Star Trek's stable wormhole near Deep Space Nine to Interstellar's visually stunning Gargantua, popular culture has embraced wormholes as the ultimate plot device. Need to get your characters across the galaxy in time for the third act? Wormhole. Want to explore themes about destiny and connection across impossible distances? Wormhole. But Hollywood's wormholes are clean, stable, and convenient. Real wormholes, if they exist, would be violent, unstable, and potentially lethal. The difference between fiction and reality, as we're about to see, is like the difference between a gentle garden gate and a raging hurricane made of twisted space-time. So what makes a real wormhole tick? And more importantly, what makes it want to kill you? To understand wormholes, we need to take a step back and appreciate just how weird space and time really are. Most of us grew up thinking of space as an empty stage where things happen, and time as a steady drumbeat marking the moments. Einstein shattered that illusion. Space and time, he showed us, are woven together into a four-dimensional fabric called spacetime. And this fabric can be stretched, twisted, and curved by mass and energy. Imagine a trampoline stretched tight. Roll a bowling ball onto it and the surface curves downward. That curve is what we experience as gravity. Now imagine two bowling balls creating two separate dips in the trampoline. What if those dips were so deep that they somehow connected underneath, creating a tunnel through the trampoline itself? That's essentially what a wormhole is, a tunnel through the fabric of space-time. But here's where the analogy breaks down, because space-time isn't really two-dimensional like a trampoline. It's four-dimensional, with 3 dimensions of space and 1 of time. A real wormhole would be a hypersphere, a shape so geometrically complex that our 3-dimensional minds can barely grasp it. Think of it this way. If you could somehow step outside our 3-dimensional universe and look down at it the way we look down at a piece of paper, a wormhole would appear as a tube connecting 2 distant regions of that cosmic sheet. But from inside the universe, all you would see is what physicists call the throat, a spherical region where space seems to curve inward on itself. The mathematics are beautiful and terrifying. Einstein's field equations don't just allow for wormholes under certain conditions, they practically demand them. The same geometric principles that govern the orbit of planets and the bending of light around massive stars suggest that space-time could fold in on itself, creating shortcuts between the most distant corners of reality. But there's a catch. Actually, there are several catches, each more problematic than the last. The first is stability. Most wormhole solutions in Einstein's equations are what physicists call non-traversable. They exist for only an instant before collapsing. Imagine trying to crawl through a tunnel that's collapsing faster than the speed of light. You wouldn't make it halfway before being crushed by the very space-time you were trying to travel through. In 1962, physicist John Wheeler and his student Robert Fuller proved that any wormhole formed by ordinary matter would collapse so quickly that not even light could pass through it. The tunnel would pinch off in less time than it takes light to cross from one mouth to the other. This is where Kip Thorne's 1988 breakthrough becomes crucial. Thorne realized that you could, in principle, hold a wormhole open, but only with something that doesn't exist in our everyday experience. You'd need what physicists call exotic matter. And exotic matter, as we're about to discover, makes the impossible seem merely improbable. Let's talk about exotic matter, because this is where wormhole physics gets truly bizarre. To understand exotic matter, we first need to understand normal matter. Everything you've ever touched, breathed, or observed is made of particles that have positive mass and positive mass and positive energy. This sounds obvious, but it's actually a fundamental constraint on how our universe works. Positive energy creates attractive gravitational fields. It pulls things together. But to hold open a wormhole, you need something that pushes things apart. You need matter with negative energy density. And not just a little bit, you need vast quantities of it threading through the throat of your wormhole like some kind of cosmic scaffolding. This exotic matter would have properties that seem to violate our basic intuitions about reality. It would have negative mass, meaning it would fall upward instead of downward in a gravitational field. If you tried to push it, it would push back in the wrong direction. If you tried to heat it up, it would get colder. It sounds like science fiction, But quantum physics suggests that exotic matter isn't impossible, just incredibly difficult to create and control. In 1948, Dutch physicist Hendrik Casimir predicted that empty space itself contains negative energy. If you place two metal plates very close together in a perfect vacuum, the quantum fluctuations of space will create a tiny attractive force between them. This Casimir effect has been measured in laboratories, proving that negative energy densities can exist, at least on microscopic scales. But here's the problem. The amount of exotic matter you need to hold open a human-sized wormhole is staggering. We're talking about negative mass energy equivalent to the mass of Jupiter, concentrated in a region smaller than an atom, and somehow arranged in a perfect configuration that extends throughout the throat of the wormhole. Current technology can't even reliably create microscopic amounts of negative energy, let alone the cosmic quantities required for a traversable wormhole. It's like asking someone in the Stone Age to build a nuclear power plant. But let's say we somehow solve the exotic matter problem. We've figured out how to manufacture Jupiter masses of negative energy and thread them through our wormhole. Are we ready to take that first step through? Not even close. The second major problem is what happens to you, the poor, fragile biological entity trying to pass through a region where space-time itself is twisted into impossible geometries. Remember, a wormhole isn't just a tunnel through space. It's a tunnel through space-time where the very concepts of distance and duration break down. The tidal forces inside a wormhole would be immense differential gravitational effects that could stretch your body like taffy or compress it like a grape in a hydraulic press. And that's assuming you could even enter the thing in the first place. The mouth of a wormhole would be a sphere of violently curved space-time, possibly surrounded by regions of exotic matter with properties that might be toxic to ordinary matter like your body. Then there's the radiation problem. Any real wormhole would likely be blazing with high-energy particles and electromagnetic radiation. The exotic matter holding it open might generate deadly forms of energy that have no earthly equivalent. You might be incinerated before you even reach the throat. But perhaps the most disturbing problem is quantum mechanical. In the late 1980s, physicists began to realize that quantum effects might make wormholes inherently unstable, even with perfect exotic matter scaffolding. When you try to send information through a wormhole, and remember, you are information in the form of complex arrangements of atoms, the quantum fluctuations in the wormhole's throat might amplify into a devastating feedback loop. The wormhole could collapse the instant you try to use it, trapping you in a region of space-time that's ceasing to exist. Stephen Hawking called this the chronology protection conjecture, though it applies to more than just time travel. The universe, Hawking suggested, might have built-in mechanisms that prevent paradoxes and impossibilities. Wormholes might be mathematically allowed by Einstein's equations, but quantum mechanics might ensure they can never actually be used. So we have three enormous problems. We need exotic matter we can't make. We need to survive conditions that might be unsurvivable. And we need to overcome quantum effects that might make the whole enterprise impossible. But here's the thing about impossible problems. Sometimes they have unexpected solutions. Despite all the problems we've just discussed, some of the world's most respected physicists haven't given up on wormholes. In fact, recent developments in quantum physics and cosmology have opened up entirely new possibilities for creating traversable shortcuts through space-time. Let's start with the exotic matter problem, because there might be a loophole we haven't considered. In 1999, physicist Matt Visser at Victoria University of Wellington published a paper that changed how scientists think about wormhole engineering. Visser showed that you might not need exotic matter throughout the entire wormhole structure. Instead, you might be able to get away with a thin shell of exotic matter right at the throat, with normal matter handling the structural support everywhere else. This is like discovering that you don't need to build an entire bridge out of unobtainium. You just need unobtainium bolts at the critical stress points. Even better, Visser calculated that you might need far less exotic matter than previously thought. Instead of Jupiter masses, you might get away with just a few kilograms of negative energy matter, precisely arranged at the wormhole's narrowest point. A few kilograms is still impossibly beyond our current technology, but it's not impossibly beyond our current imagination. Meanwhile, other physicists have been exploring even more exotic possibilities. What if you could create a wormhole without exotic matter at all? In 2013, physicist Juan Maldacena at the Institute for Advanced Study, working with Leonard Susskind at Stanford, proposed a radical idea. They suggested that wormholes might be intimately connected to quantum entanglement, the spooky action at a distance that Einstein famously disliked. Their E equals EPR conjecture, where ER stands for Einstein-Rosen bridges, and EPR stands for the Einstein-Podolsky-Rosen paradox of quantum. Entanglement suggests that every pair of quantum entangled particles might be connected by a microscopic wormhole. If this is true, then wormholes aren't just mathematically possible. They might be fundamental features of reality, woven into the quantum fabric of space-time at the smallest scales. This opens up an incredible possibility. Instead of building a wormhole from scratch, maybe we could find ways to expand existing microscopic wormholes into macroscopic tunnels. Imagine being able to take two quantum entangled particles and somehow inflate the invisible wormhole connection between them until it's large enough for a spaceship. It sounds like magic, but the mathematics are surprisingly robust. In 2017, physicists at Harvard and MIT actually created a simulation of a wormhole using quantum computers. They took 7 quantum bits, arranged them in a specific pattern, and watched as information teleported from one side to the other through what appeared to be a simulated wormhole in the quantum system. It wasn't a real wormhole, nothing physical traveled through space-time, but the quantum information behaved exactly as if it had passed through a wormhole tunnel, following the same mathematical rules that govern theoretical wormhole traversal. This kind of quantum simulation is giving physicists new insights into how wormholes might work, and potentially how they could be created or controlled. But even if we solve all the theoretical problems, we still face the practical question: how much energy would it take to build a real wormhole? The numbers are mind-bending. Creating a human-sized wormhole might require as much energy as our sun produces in a year, focused into a region smaller than an atom, sustained for the entire duration of the wormhole's existence. Even with perfect efficiency and perfect technology, you'd need the energy output of an entire stellar civilization. For comparison, humanity currently uses about 580 million terajoules of energy per year. Creating a stable wormhole might require 1,026 times more energy than that. It's not just beyond our current capabilities. It's beyond the capabilities of any civilization confined to a single planet. You'd need to be what physicists call a Type 2 civilization on the Kardashev scale, a species capable of harnessing the entire energy output of their host star. Humans are barely a Type 1 civilization, able to harness only a tiny fraction of our planet's available energy. But here's the fascinating part. Nothing in physics says such energy levels are impossible to achieve. They're just impossible for us right now with our current technology and our current understanding. Which brings us to an even more intriguing question. If wormholes are possible, and if sufficiently advanced civilizations could build them, what would that mean for the nature of space, time, and causality itself? Here's where wormhole physics becomes genuinely unsettling, because it turns out that any technology capable of creating shortcuts through space might automatically create shortcuts through time as well. The reason has to do with Einstein's most famous insight. Space and time are not separate entities, but aspects of a unified four-dimensional fabric. When you curve space, you inevitably curve time. When you create a tunnel through space, you might be creating a tunnel through time as well. Here's how it could work. Imagine you've built two wormhole mouths, the entrance and exit of your cosmic tunnel. Initially, they're synchronized. A clock at mouth A shows the same time as a clock at mouth B. Now, take mouth A on a high-speed journey through space, while leaving mouth B at rest. According to Einstein's theory of special relativity, time passes more slowly for the traveling mouth. When mouth A returns to its starting location, the clock at mouth A will show less elapsed time than the clock at mouth B. But here's the kicker. The wormhole tunnel itself exists outside normal spacetime. From the perspective of someone traveling through the wormhole, the journey between mouth A and mouth B is instantaneous, regardless of how much time has passed in the outside universe. This means you could enter mouth A and exit mouth B before you entered mouth A, relative to outside observers. You've just traveled into the past. The implications are staggering. With a time-capable wormhole, you could potentially travel back and prevent your own birth, creating the famous grandfather paradox. You could deliver information to the past, creating causal loops where effects precede their causes. This is where Stephen Hawking's chronology protection conjecture becomes crucial. Hawking argued that the laws of physics must somehow prevent these kinds of paradoxes, even if we don't yet understand how. One possibility is that quantum effects would destroy any wormhole the instant it becomes capable of time travel. The quantum vacuum might become unstable in the presence of closed time-like curves, generating massive amounts of destructive energy that would vaporize the wormhole's exotic matter scaffolding. Another possibility is that time travel through wormholes might be possible, but self-consistent. Maybe the universe has a way of ensuring that any time travel automatically creates the conditions that make that time travel necessary in the first place. You can travel to the past, but you can't change it. You can only fulfill it. Some physicists have proposed even stranger solutions. Maybe consciousness itself plays a role in preventing paradoxes. Maybe free will is an illusion, and any apparent choice to create a paradox would be physically impossible to make. Or maybe, and this is perhaps the most disturbing possibility, maybe paradoxes are allowed, and time travel through wormholes would create branching timelines or parallel universes. You could kill your grandfather, but you'd be doing it in a different timeline than the one you came from. These aren't just abstract philosophical questions. If wormholes are real, if they can be built, and if they can be used for time travel, then these paradoxes represent genuine physical constraints on how such devices could operate. But even setting aside the time travel complications, the mere existence of traversable wormholes would revolutionize our understanding of the universe in ways that are hard to imagine. Think about it. If faster-than-light travel through wormholes is possible, then the cosmic speed limit imposed by light might not be as fundamental as we thought. The universe might be far more connected than it appears. Distant galaxies might be as accessible as neighboring cities. And if microscopic wormholes really do exist at the quantum level, as the E equals EPR conjecture suggests, then every particle in your body might be connected to particles everywhere else in the universe through an invisible network of space-time tunnels. You might be more connected to the cosmos than you ever imagined. So where does all this leave us? Are wormholes science, or are they science fiction? The honest answer is, we don't know yet, but we're getting closer to finding out. In laboratories around the world, physicists are pushing the boundaries of what's possible with quantum mechanics and exotic matter. The Casimir effect, that tiny attractive force between metal plates in a vacuum, has been measured with increasing precision, confirming that negative energy densities really do exist in nature. At CERN, the European Particle Physics Laboratory, researchers are probing the fundamental structure of space-time with the Large Hadron Collider, searching for signs of extra dimensions and exotic physics that might be relevant to wormhole formation. In 2022, researchers at Google, working with physicists at Caltech and Harvard, created the most sophisticated quantum simulation of a wormhole to date. They used Google's Sycamore quantum computer to model the behavior of information passing through what they called a quantum wormhole. Again, this wasn't a real wormhole. No actual space-time was curved. No actual tunnel was created. But the quantum information behaved exactly as theoretical physics predicts real wormhole information would behave. It disappeared from one part of the quantum system and reappeared in another part, with all the characteristics of having traveled through a wormhole tunnel. These simulations are giving physicists new insights into the quantum mechanics of wormhole formation and stability. They're testing theoretical predictions in ways that would be impossible with real wormholes, even if we could build them. Meanwhile, astronomers are searching for observational evidence of natural wormholes in the universe. If wormholes exist, they might leave subtle signatures in the cosmic microwave background radiation, the afterglow of the Big Bang. They might create distinctive gravitational wave patterns when they form or collapse. They might even be mistaken for black holes, since the external gravitational effects would be similar. In 2019, a team of astronomers proposed that the supermassive black hole at the center of our galaxy might actually be a wormhole. They suggested that the strange behavior of stars orbiting near Sagittarius A** could be explained if some of those stars were occasionally passing through a wormhole mouth, rather than simply orbiting a black hole. The evidence is far from conclusive, but it illustrates how seriously mainstream scientists are taking the possibility of wormhole detection. But perhaps the most exciting development is happening in the realm of quantum gravity, the long-sought theory that would unify Einstein's general relativity with quantum mechanics. String theory, loop quantum gravity, and other approaches to quantum gravity all suggest that space-time itself might have a discrete, granular structure at the smallest scales. If this is true, then wormholes might not be smooth tunnels through continuous space-time, but rather discrete connections between quantum bits of space and time. This quantum perspective on wormholes might solve some of the classical problems we discussed earlier. If space-time is made of discrete quantum units, then the violent curvature at a wormhole throat might be naturally regulated by quantum effects. The exotic matter requirements might be reduced or eliminated entirely. Some physicists even speculate that our entire universe might be connected by a vast network of microscopic wormholes, constantly forming and dissolving at the quantum level. This space-time foam, as John Wheeler called it, might be the fundamental substrate from which larger wormholes could emerge. But we're still incredibly far from actually building a macroscopic traversable wormhole. The energy requirements remain astronomical. The exotic matter requirements remain unsolved. The quantum stability problems remain unresolved. Current estimates suggest that even a civilization capable of harnessing the energy of an entire star might struggle to create a stable wormhole large enough for human travel. You might need the resources of an entire galactic civilization to make it practical. And even if you could build one, would you dare to use it? This brings us to perhaps the most profound question raised by wormhole physics. If we could build these cosmic shortcuts, should we? Think about what it means to be human in a universe where distance and time can be circumvented. Our entire evolutionary history has been shaped by the constraints of space and time. We developed language to communicate across distances too great for touch. We developed memory to carry the past into the present. We developed planning and hope to bridge the gap between present and future. What happens to human nature when those gaps disappear? If you could step through a wormhole and visit any place in the universe instantly, would exploration lose its meaning? The journey has always been as important as the destination in human experience. The anticipation, the preparation, the gradual revelation of new landscapes, these are fundamental to how we process discovery. Would instant travel eliminate the romance of distance? Would it make the universe feel smaller, more mundane? And what about the more disturbing possibilities? If wormholes can be used for time travel, then the entire concept of linear causality, cause-following effect and orderly sequence, might be an illusion. Our legal systems, our moral frameworks, our basic understanding of responsibility and consequence are all built on the assumption that the past is fixed and the future is open to influence. Time-traveling wormholes would shatter that assumption. But there's an even deeper philosophical issue, the question of identity and continuity. When you step into a wormhole, what exactly is making the journey? Your body is a collection of atoms arranged in a specific pattern. During the passage through twisted space-time, those atoms would be subjected to forces and field effects that have no equivalent in normal experience. Would you emerge from the other side as the same person who entered? Or would you be a copy, similar but not identical, carrying the memories but not the true continuity of the original? This isn't just abstract philosophy. In quantum mechanics, the act of measurement can fundamentally alter the system being measured. The intense quantum effects inside a wormhole might measure your every particle in ways that change their properties. You might survive the journey through a wormhole, but the person who emerges might be subtly different from the person who entered, changed in ways too small to notice, but too fundamental to ignore. And then there's the question of what we might find on the other side. Most discussions of wormhole travel assume that the other end leads to another location in our universe, or perhaps to another time in our universe's history. But what if wormholes can connect to completely different universes, alternate realities with different physical laws, different histories, different possibilities? The mathematics of general relativity allow for this. A wormhole could theoretically connect to a universe where the speed of light is different, where gravity works differently, where the fundamental constants that govern chemistry and biology have different values. Stepping through such a wormhole wouldn't just be traveling to another place. It would be traveling to another version of reality itself. Would you still be human in a universe with different physical laws? Would your thoughts still make sense in a reality where quantum mechanics works differently? Would your body even be stable in a universe where the electromagnetic force has a different strength? These questions push us to the very limits of what it means to exist as conscious beings in a physical universe. But perhaps that's exactly why wormholes are so compelling as both scientific concepts and philosophical thought experiments. They force us to confront the most basic assumptions about reality, identity, and possibility. They ask us to imagine what we would do if the impossible became merely improbable. We began this journey standing at the edge of an impossible tunnel through space-time, wondering if we could ever step through to the other side. Now, having explored the physics, the problems, and the possibilities, we find ourselves in a strange position. Wormholes might be real. The mathematics of our most successful theory of gravity says they could exist. Quantum mechanics suggests ways they might be created or controlled. Advanced civilizations might already be using them, but they remain just beyond our reach, taunting us with their proximity to possibility. Maybe that's as it should be. Maybe some discoveries are so fundamentally transformative that they require not just scientific advancement, but philosophical and spiritual evolution as well. Think about it. Every major breakthrough in human understanding has required us to expand our conception of what is possible. The realization that the Earth is round forced us to reimagine our place in space. The discovery of evolution forced us to reimagine our relationship to other life forms. The development of quantum mechanics forced us to reimagine the nature of reality itself. Wormholes would force us to reimagine everything. If we ever do figure out how to build traversable wormholes, we'll be facing the most profound transformation in human experience since we first looked up at the stars and wondered what they were. We'll have to grapple with questions that have no historical precedent. How do you govern a civilization spread across multiple galaxies, connected by instantaneous travel? How do you maintain human culture and identity when the constraints that shape that culture have been removed? How do you prevent the misuse of technology that could unravel causality itself? These aren't problems for engineers. These are problems for philosophers, ethicists, and perhaps entirely new categories of human thought we haven't invented yet. But here is what makes the wormhole question so fascinating. We don't have to wait for the technology to start thinking about these issues. The mere possibility of wormholes is already expanding our understanding of what the universe might be like. Every time a physicist publishes a paper on traversable wormholes, every time a quantum computer simulates wormhole information transfer, every time we detect exotic matter in a laboratory, we're taking small steps toward a future that might include cosmic shortcuts through space-time. And every step forces us to confront a fundamental question about human nature. Are we brave enough to use the ultimate transportation technology? Are we wise enough to handle the power to reshape space and time? Are we ready to discover what lies on the other side of the cosmic doorway? Standing at the edge of that shimmering tunnel of twisted space-time, looking through to another world, another time, another version of reality entirely, would you take that step? The universe, in its infinite mystery and possibility, is waiting for our answer. Perhaps someday, sooner than we think, we'll be ready to give it.